Oh, yes, good, thank you.
First message.
Oh, yes. Oh, true.
If you read it, we'll talk about
Yes.
it. Like, wait, I didn't realize we did
Right, right. Well, all of the dates might be a bit aspirational. I'm always tempted when I write your name to add a second I. Somehow I want it to be French. Humilier.
You're not the first person to start thinking.
Yes, the answer is yes. You tell me.
Yes,
yeah.
Great.
Also agree.
Great. I'm glad we're agreeing.
Well, whenever, I'm happy to go whenever.
Pitching Liam Fitzpatrick's talk, which is on a topic that is deeply connected to my CFT book.
Ah,
Yes.
I'm not sure the strategy.
I don't think it's going over, but there is the.
Well, I appreciate your sacrifice, Chester.
Hopefully this will be my ice cream version.
I would not count on that either. Then I would skip the top. The other one. Yeah. I don't think there will be any strings around. Yeah. Thankfully.
Did you PhD in this?
Yes.
Should I introduce?
I don't know how much introduction do you normally do. Oh, yes. Again.
Right. So welcome everyone to Harvard CMSA Quantum Math Physics Seminar Series. Very happy and honored to invite Seth Koren. He is very enthusiastic promoting new concepts in quantum field theory to beyond standard law physics and beyond the usual particle physics we know. And he did a PhD at the UCSB and then postdoc at Chicago, right now at the Notre Dame. He's also very interested in quantum matter phenomena, so I'm pretty respect and enjoy talking to Seth. And please let me remind you, feel free to ask questions during this talk. That's welcome, sir.
Thank you, Juven. Thanks everyone for coming. Thank you to Juven and the CMSA for having me. And indeed, I'm a bit on the fringes in terms of the normal sorts of talks in this series, and also this is a different, more informed on these topics audience than I normally have. So I sort of mash a bunch of slides together. I'll skip through some of the introductory things I normally say to particle physicists. My plan, I think, is to sort of go over the generalized symmetries of the standard model in particular, because I think I want to start thinking about the use of generalized symmetries in particle physics. The standard model is very very good place to start, and then talk a bit about this paper from last year, although I think one of my collaborators at least presented it in the seminar series a while ago, but that will nicely set up some forthcoming work that we are putting out. Okay, so for particle physicists, I give some very brief motivating why we should think about higher form symmetries just as extending our notion of global symmetries acting on local operators to actions of global symmetries on extended operators, which often appear in our particle physics theories, like Wilson lines or cosmic strings, and usually we ignore them often when we're thinking about BSM physics, but that's really to our detriment, because often there is information there, and in particular, the very interesting feature that I'm really going to be playing around with, although I think there's a lot more to say, because there's some interesting things in this space. But if we have some familiar zero form symmetry that acts on particles, then you break such asymmetry by adding some charged operator to Lagrangian, like in my Majorana mass for neutrinos breaking lepton number. But in contrast, for these higher form symmetries that act only on extended operators, I can't put anything into the Lagrangian that will break that symmetry. So these symmetries get broken only by the appearance of new dynamical degrees of freedom at some UV scale, basically when these operators are no longer topological. And so, this is in our study of symmetries as particle theorists, this is a fascinating new sort of feature. And in particular, the way I'm going to use this is if we find some scenario where a higher form symmetry is in some way intertwined with familiar zero form symmetry, we have some particular symmetry defect operators that act on both kinds of operators, then we will be able to learn from the infrared about the fate of our zero form symmetry at some UV scale when new dynamical degrees of freedom enter. And this will be extra information that is always there in our theory, and it serves us to learn what it has to tell us. Okay, so I think everyone here is familiar enough with higher form symmetries. For particle physicists, I like to just tell them one form symmetry is really just Gauss's law, and this is some more detail on exactly what I've said that I'm going to skip through. And in particular, I think is also known to this audience, but I'm going to be making use in the things I'm going to tell you about of non-invertible symmetries, which for the types of four-dimensional non-invertible chiral symmetries that I'm going to make use of, I just think about as being involved in having an ABJ anomaly with some gauge group where you don't, for topological reasons, have instantons on four-dimensional flat space where we know we approximately live. And so that was the sort of motivating example for this work from Clay and Cantaro, and also from Shuhang, the Stony Brook group, to explore four-dimensional non-invertible symmetries about a year ago. Now let me skip through the construction of non-invertible symmetries in detail. But again, the point just to emphasize will be, we're going to have some scenario in the infrared where you have an ABJ, global symmetry has an ABJ anomaly, so you think that it should be broken, but the gauge group does not have any instantons on R4 or S4 after you regulate it. And that's going to tell us that there is a non-invertible symmetry, a subtler sort of symmetry that is going to act both now on local operators and on tophlons. And that's going to, that intertwining is going to tell us that when we break the magnetic one-form symmetry, that's going to communicate some non-perturbatively small breaking of the zero-form symmetry. It tells you about some interesting way, straight just from an infrared analysis, that some global symmetry in your theory, global zero-form symmetry in your theory, might be broken only by an exponentially small amount. and because we are often curious as particle physicists about the origins of small numbers, small breakings of asymmetry, I'm going to hopefully convince you in some examples that understanding these infrared symmetries of our theory can actually lead us to some UV models of BSM physics, where instantons in the UV can resolve some infrared naturalness issues. In particular, I emphasize that these theories will be very close to the standard model. And so in some sense, could have easily been discovered anytime in the last 40, 50 years. And so this better understanding of the infrared symmetries leading us to these nice models, I think it really is a great show of the uses, the possible benefits to us as particle physicists in paying attention to what the formal field theorists are thinking about and understanding these more subtle notions of symmetry. Okay, let me, yeah.
How can you kind of like just clarify more?
Yeah.
Because the sentence of the interline between the breaking and the new one point is the relation of small breaking of a zero point symmetry. Can you make it? Will you make it more?
Yeah, let me let me skip any construction of the actual defects. But the point and really the great example of this is from Katie and John and Matt and Gigi a couple years ago. We have some non-invertible symmetry defect operator that acts now both on local operators and on some Tuft loop, right? And so if I have some local operator, which is protected only by my non-invertible symmetry, then when I introduce into my theory some magnetic monopoles, which can cut this Tuft line, the non-invertible symmetry must properly be broken. It acts on something which is no longer truly topological now. Okay. And so since that was the only thing protecting my local operator from being generated, it must be generated now. But we can think in any specific theory, and I'll show particular theories where we'll see how this comes from. But if you can think in general about some UV completion where the monopoles are weakly coupled Tuft-Polyakov monopoles, then we can estimate what this breaking from loops of monopoles will be. I just said John's name, so great timing. So these monopoles have a mass that's like the symmetry breaking scale over the gauge coupling. Again, for simplicity, I'm just thinking about some weak coupling Tuft-Polyakov monopoles, which are the things that are going to break these Tuft lines. A mass of the symmetry breaking scale over G. The cutoff of this theory, the mass of the W bosons, the lightest new degrees of freedom, will be the symmetry breaking scale times the gauge coupling. And this local operator that was only protected by the non-invertible symmetry must be generated by loops of monopoles, which give a penalty of the monopole action in the coefficient they generate.
Just make sure G here is much larger than order 1.
G is much smaller than order 1. So weak coupling, so I can think very perturbatively just about monopoles.
So what's the cutoff here?
The cutoff of my, so I'm imagining I have an infrared theory that had a non-invertible symmetry, and I'm thinking about what the effects will be of some UV physics that includes these magnetic monopoles. So I'm doing a calculation in my low energy EFT of what I expect from a loop of magnetic monopoles. I'm calling this a cutoff just to, I'm using some world line monopole action reasoning that the monopole action should be roughly the mass of the monopole times some small time over which that monopole anti-monopole pair pops into existence and then propagates before annihilating again. And if I'm an infrared person, I should think those times are of order the cutoff of my infrared theory. That's the new scale over which new stuff can come in and propagate. And so this is just some approximate infrared reasoning to tell you why you should expect from the infrared that the corrections, the violations of the non-invertible symmetry will scale in this minus something over g squared. It's like a non-perturbative gauge theory sort of correction. But I don't need to rely on this reasoning. We'll see how that happens in the UV theories that I write down. But in terms of my interest for model building, the plan is that if we find some infrared theory that has a non-invertible symmetry protecting some operator that I want to explain why it's small, then I want to embed that infrared theory in a UV theory that includes magnetic monopoles, and I should expect from this general reasoning to find an exponentially small violation of that symmetry. And we'll see that happen. Okay, I want to go over a bit the standard model, because like I said, if we want to think about the possible uses of generalized global symmetries in particle physics, the standard model is the right place to start. So what are the one-form symmetries of the standard model? Well, we know the Lie algebra is SU3 cross SU2 cross U1, and from the U1 factor and not having light magnetic monopoles included in the standard model, we know that hypercharge has a magnetic one-form symmetry. And then what about an electric one-form symmetry? Well, as probably this audience is familiar and was explained very nicely by David Tong, although not quite in this language, we don't know if we have an electric one-form symmetry. Because we don't actually know the gauge group of the standard model. What we've seen so far does not uniquely determine. This reasoning is probably familiar with everyone, but because it will come up later in some interesting BSM extensions in a different sort of way, let me just briefly remind you that there are certain center transformations living in the Z3 center of SU3, the Z2 center of SU2, and U1, which don't actually act on any of the standard model fields. Very simply, if I consider a Z2, which is in the diagonal of the center of SU2 and hypercharge, so it acts like -1 on all of the fundamentals and like a pi location for hypercharge, right? This, then it so happens to be the case, and from the infrared, it seems like it didn't have to be that way. It just so happens that all of our SU2 fundamentals have odd hypercharge, and all of the SU2 singlets have even hypercharge. So together, this Z2 in the diagonal of these two centers doesn't actually act on any of the standard model fields. So then perhaps it's the case that it's not actually part of the gauge group. And that's what this question of the global structure of the standard model gauge group is. It might be that the gauge group is not just SU3 cross SU2 cross U1, but has some non-trivial quotient by a discrete subset of the subgroup of the center. And if it does, if it does not have a quotient by the entire subgroup that could be quotiented, this Z6, then there is an emergent electric one-form symmetry of the standard model. And of course, a very good question you should ask is how we could tell between these different options. And if all I have access to is the standard model particles, then it's indeed very difficult. Essentially, you need to discover the magnetic monopole, something like that. Recently, there was a flurry of work by Matt here and the Stony Brook group and a Chicago group on if I add an axion to this story, then you have an extra handle, and then you can look at the quantization of the axion's couplings, and that tells you about the global structure. Really, this is sort of repurposing a feature that David Tom had already talked about the periodicity of the various theta angles. Just you sort of bring that to life more when you have an axion. And let me advertise some work with Adam Martin at Notre Dame, also making use of something that David Tom and these people also know, but there's something much more mundane, which is that if we don't actually have this Z6 quotient, then you should think of the fact that the standard model is consistent with the possibility of a Z6 quotient as just being some sort of accident of the chiral spectrum of the standard model that we've seen. And I think we have, in general, every reason to expect that once we, hopefully at the LHC or some future collider, observe some particles that are vector-like representations of the standard model gauge group, we'll see the entire charge lattice. And so this would be, if you discover fractionally charged particles at the LHC or elsewhere, that would tell you that in fact we don't have the Z6 quotient. We just have, well, something smaller. The basic point that we'd like to make, aside from exploring a bit about what these look like in the standard model EFT and such, is just that this is a very high stakes sort of thing to look for. It seems like not enough experimental effort is directed that way, because if you discover such a fractionally charged particle at the LHC, you rule out SU5 grand unification from LHC energies, because SU5 grand unification necessarily produces the Z6 quotient, and so it tells you you cannot have any fractionally charged particles. Is there a question?
Yeah, I guess. In these axionic fluids,
Yeah.
how much do I need to measure axion as a probe? Like surely I don't know how to explore the axion field space. So I mean, if I'm thinking about the types of quantities that I would measure,
yeah,
measure like G again,
yeah,
maybe the mass of the axion that exists, and
the coupling to GD dual.
then a couple of your G.
Yeah.
If I could measure.
Sure. Yeah.
Right.
Maybe that.
So it seems like you're giving two different ways of measuring the global structure of the gauge group, either detecting a new particle, which I would say, yeah, there we go, or measuring some property about the axion.
Yeah.
Is that, could I actually determine what Q is by observing the axion?
Yeah, it's a good question. I'm not sure I've digested those recent papers completely enough to really give you a fully satisfactory answer. Certainly the different global structures imply different things about the quantization of that coupling between the axion and the gauge.
But I never actually measure. I never actually see the full field space.
Yeah. Yes.
So I guess I'm wondering, is that a detection, like a detection channel for this type of structure, or is it a yeah?
Well, the claim by a couple of the groups was that if you have the Z6 structure, you can only lie on one side of a particular ratio of the gluon and proton. So at least the conclusion seems to be if you measure that you're on the wrong side of that line, you falsify the Z6. Yeah, maybe there's some subtle difference between sort of falsifying Z6 versus discovering not Z6. That it is a little bit hairy. Yeah, sorry, I'm not having a more complete answer.
No, don't expect.
Good. Great. Okay. I'll try not to take too much time with this, but
Actually, I have a question.
sure.
So, what your question about this? You said the intertwine between the zero form symmetry and one form magnetic symmetry. Is that structure already revealed to you, or is not quite the thing you mentioned?
Oh,
I'm not sure whether these are the same thing or actually different.
no, I'd say a non-invertible symmetry.
The slide,
and the
maybe
two
one
group-
slide earlier. Go back.
Oh,
One slide earlier. Yeah, this statement, the intertwining.
yeah, well, no, I'd say a non-invertible symmetry is a different way that a zero form symmetry and a one form symmetry can be sort of intertwined. Yeah, different from a two.
Different ones. to do.
Yeah. Sort of, well, at least as a weakly coupled person, you can think about them as being encoded in different triangle diagrams.
Yeah.
That's right. And I'll get to sort of those examples in the standard model very briefly in a moment.
These triangle diagrams are for the integers.
Sorry, do they have more information? No, I'd say, yeah. Yeah. But they would tell you as a weakly coupled person, they would tell you how to construct such operators. Yeah, good. So again, this is sort of the basics of the structure of the standard model. But we have three different generations or flavors of each of our types of file fermions. And so if you turn off all the couplings, we start with a very large classical flavor symmetry. And then we write down the Euclides for the Higgs to interact, or one Higgs to interact with all of these different types of fermions. And this breaks the vast majority of this global symmetry. There is a leftover classical baryon number and one lepton number that because of electroweak instantons are broken to the continuous group B minus L and an extra discrete subgroup of lepton number, and somehow some 50 years after the standard model, last year both Juven and I decided to write papers explaining why this discrete factor is responsible for the proton being stable in the standard model. So an important thing, I think, in general to point out. And as you guys know, if I really stick to the standard model with massless neutrinos, then while in the quark sector, all you have is baryon number, in the lepton sector, also these differences of lepton family symmetries are exact symmetries, but we know from neutrino oscillations that these aren't exactly symmetries of the real world. Okay, I shouldn't spend too much time on this, although I'm happy to talk about it later. The standard model, these approximate non-Abelian parts that are broken by the Yukawa couplings are intertwined in a different sort of way with the hypercharged magnetic one-form symmetry in the form of a two group in the standard model, which Clay and I talked about last year. And this is these triangle diagrams that have two global legs, but one gauge leg. And so they don't have any sort of, they don't imply some dynamical breaking of this symmetry at low energies like an ABJ anomaly would. But this structure of the two group does tell you about the UV phase of these symmetries. And in particular, any global symmetry that is part of a U1 two group, part of a two group with U1 hypercharge must be broken when you embed hypercharge in some unified group that is going to give monopoles. And using that reasoning, you can very simply work out from these infrared charges that there are only a few possibilities for multiplet structures in a grain unified theory, at least at 0 Yukawa, just from saying that there are only a few options for diagonal flavor symmetries that might not be broken at the scale at which you introduce magnetic monopoles. Was there a question that I skipped over? No. Yeah, good. Only a few of these. And there's something more interesting as well. At 0 Yukawa, really this tells you exactly that you have these 4 possibilities for multiplet structures. You can think of finite Yukawas, in fact, as spurions of this entire 2-group structure, because the flavor symmetries are intertwined with the magnetic one-form symmetry of hypercharge. And this tells you that you can only perturb away from this multiplet structure if you have some standard model Yukawas that control the masses of some vector-like fermions. And so in particular, make those masses, rather than being at the gut scale at some Yukawa times the gut scale, potentially much lower if they're, say, vector-like leptons. So I think this is interesting logic in general, and I'd love to chat more with people about that later, but in the interest of actually getting to the main things, let me continue. There are also some approximate or exact non-invertible symmetries in the standard model. Worth mentioning that there's a particular U1 which acts on all of the right-handed fermions, which is made non-invertible because of an anomaly with hypercharge. It's approximate, and interestingly, this particular U1 is broken by any of the Yukawa couplings. Interesting to know, the Stony Brook group uses this to have some symmetry-based derivation of the decay of ion into 2 photons. I think it would be fascinating to think further about if there's some BSM use for this, but I haven't found one yet. And I'd be remiss not to mention there's also an exact, at least from the infrared, non-invertible symmetry that Juven pointed out earlier this year. If you have the standard model and some number other than exactly 3 right-handed neutrinos. And there's some interesting phenomenology there as well. In fact, much earlier, Peskin and collaborators showed that you can use this for gravitational leptogenesis to take chiral gravitational waves and turn them into a lepton asymmetry. That's interesting. Right, my final thing, because I think everyone here has heard this before, but I'll mention, well, given the standard model structure, baryon minus lepton number could be a global symmetry, or it could be a very weakly coupled gauge symmetry. And so we've needed to rely on the work of fantastic experimentalists who've gone out and measured tons and tons of different things to tell us that indeed there isn't any very weakly coupled B minus L photon doing some 5th force at exactly 0 energy, but a discrete subgroup of B minus L could very well be gauged and entirely unbroken. A real extra gauge symmetry of the standard model fermions in the far infrared. This is an extension, in some sense, the simplest extension of the standard model you could imagine. It doesn't have any free parameters, no new degrees of freedom, and for aficionados of generalized global symmetries, this would come along with a magnetic 2-form symmetry of the standard model in the infrared. So I think it's just worth thinking much more about this B minus L BF theory in general. I did, as you guys I think know, also point out that particularly for n equals 6, they could have some interesting connection to the cosmological lithium problem. But let me actually get to what I want to do today. So my raison d'être, joie de vivre, is model building. The standard model is fantastic. It's a really interesting. There's lots of interesting structure there that I've gone through, but it's an incomplete understanding of the universe, and not just because we know there are things that the standard model doesn't explain, of course, but also that there are features of the standard model that look weird, that you have to put in by hand. And as good reductionists, we should search for some more fundamental theory that, rather than having those be inputs to the theory, explains their origins. But where exactly to look? Of course, as any particle physicist listening knows, there are many such BSM models that people think about, and it makes getting into particle physics in the current era very difficult. But to make things easy for you and for myself, I'm thinking about starting with just the simplest class of models which go beyond the standard model, which in my view is to gauge some of the approximate symmetries of the standard model. And to remind you, this is really the class of all of the classic grand unified theories, some of which were discovered here. For example, the standard model fermions have an approximate SO10 symmetry that's broken by, say, all of the gauge couplings being different. So I'm going to explore, the class of things I'm going to explore, although I'm going to explore gauging some of the family symmetries of the standard model. In my view, you should really think of this as the class of unified theories, which are very natural extensions of the standard model to think about. And so I am going to be thinking about multiple generations. And I'll remind you, I think this is one of the features of the standard model, which we would most desperately like an explanation to. I would most desperately like an explanation to. We're all made out of first generation stuff. And for some reason, we learned now nearly 90 years ago that there's extra stuff around, that we don't need to explain the structure of matter on Earth. But nonetheless, we have second and third generations of quarks and leptons. And somehow we haven't, to my knowledge, really learned much since Robbie first asked who ordered that about the muon. And if you guys have no other ideas about this that I haven't written here, please do tell me. I think one of the most interesting observations that has been made, although it's not a silver bullet, but if you just sort of uplift the standard model gauge group to 6 dimensions, then there are extra global sort of Witten type anomalies of, say, SU2 that you need to care about, and that in particular, those no longer cancel within a single generation. And so that could be some sort of answer for why you have to have multiple generations. It's a bit weird to go to 6-dimensional field theory. It's difficult in general, and it's not obvious that you want to just have the standard model being true in 6 dimensions, but it's something. Because people say it, I've mentioned if you just uplift the standard model electroweak to SU3 cross U1, you can embed the standard model fermions in a sort of non-universal way. Frampton, I think in particular, has tried a lot to tout this as some sort of explanation. You could also do it more universally, so it's not, in my opinion, a great one, but yes, please.
So I actually have a comment about this, the bullet point about the 60 jump to the global anomaly.
Yeah.
So in the old days, they checked the homotopy group. And right, and I think from the homotopy group calculations, you can get some anomaly index like from the homotopy group.
Yeah.
And there's something like Z12, something show up. But now that we know the global anomaly is not captured by homotopy group, by cobordism group.
Okay.
And at some point, actually, I checked this. It turns out those anomalies are not quite there. In a sense, I think those anomalies vanish.
Oh.
And I kind of doubt whether this argument is robust.
Okay.
Basically.
Yeah, that would be.
That's just something I want to tell you.
Yeah.
Because
Thank you.
I look into those references at some point and I find, oh, that's interesting to constrain the number of a generation. But when I check the global anomaly from cobordism, I don't think they are there.
Interesting.
Yeah, I think that's a comment.
Yeah, no, that's fascinating. Yeah, if that's right, that would be, it would be great to have that point simply made somewhere in a way accessible to particle physicists.
Yeah, I think the rough statement is that Witten anomaly was checked for pi4 of SU2.
Yeah.
There's pi4 of S3 and there's a D2. But that one is survived when you check cobordism group, which is the cobordism group by dimensions with spin times SU2. And there's a Z2 times Z2 index. Oh, sorry, actually there's a one Z2 and there's another Z2 if you consider spin and SU2 should be something SU2 anomaly. And you can do the same calculation for sig B that you check pi6 of SU2 and pi6 of the standard model group.
Right.
You might get something like Z12 or something. But if you check cobordism group, which is TP, so omega, a cobordism group 7 dimensions, usually you don't get anything.
Okay.
Yeah, that argument sounds interesting in the past, but I doubt this argument will work.
Okay.
Anyway,
Okay. No, really fascinating.
I can spend
Absolutely. Yeah, I'd love to chat further later. A better, well, not that, another sort of answer, maybe a more correct sort of answer, and the sort that I've been exploring, is to find some sort of physical effect that really you can only get with 3 generations or with multiple generations in general. And I think we had, for some decades, you could have held on to what would have been a great answer, which is that you can only get CP violation in the CKM matrix, the matrix of quark mixing, if you have at least 3 generations. It vanishes identically for 1 or 2 generations. And it was a beautiful theory of nature that was proposed in the 80s, was electroweak baryogenesis, that you could explain matter-antimatter asymmetry really just using the standard model ingredients. And that would have been a fantastic explanation for why we needed 3 generations. But unfortunately, we know now that does not work, is not realized as initially envisioned back in the 80s. So it was not a fantastic answer. I already mentioned multiple generations are responsible for proton stability of the standard model, but also not a great answer because the proton, even with 1 generation, would be very long-lived. But I like this sort of line of thinking, and it motivates me to think about possible effects you can have beyond the standard model, really only when you have multiple generations, especially if you can find something interesting for 3 generations. And before I actually get to the meat of my talk, I'll mention that Sam and I have some work in progress on a certain model of flavor that you can only do for 3 generations, because if you give the Higgs a flavor index, then you can write an invariant Yukawa using the Levi-Civita symbol, which makes use of the fact that 3 is special because a Yukawa interaction has 3 fields. And so this is a bit of fun. But yeah, it has some interesting properties as well. And Sam and I will hopefully soon have something out to tell you more about that. Okay, but what I actually want to do, this observation that we made in this paper last year with, I think I forgot to say my collaborators at the title slide, so with Sung Woo and Clay Cordova and Kentaro Omori, the observation we made is that this very well studied theory of BSM physics, a gauged L mu minus L tau symmetry, one of these anomaly-free global symmetries of the standard model. When you gauge L mu minus L tau, there is an extra class of anomaly diagrams that you should look at, ABJ anomaly diagrams that have the 2 gauge legs. And indeed, there is a mixed anomaly with this other global symmetry, the other lepton family difference symmetry. -1 is the coefficient, right? And this indeed implies that these theories that had been studied for some 30 years and many hundreds of papers have in fact a non-invertible symmetry that protects neutrino masses. And the nice way to see that it really protects all of the neutrino masses is, okay, so it looks like it's just with Le minus L mu, but Le minus L mu, if you subtract a gauge charge, well, because -2 is equal to 1 mod 3, then in fact, this includes, overlaps with a Z3 subgroup of actual lepton number. Looks like this, +1 for the left-handed leptons, -1 for the right-handed guys. And this disallows you or protects the Majorana mass term. Okay, and of course, all the particle physicists in the room know that one puzzle of the standard model is why the standard model, why the neutrino masses are so much smaller than all of the other fermion masses. So it's very interesting to find some subtle symmetry structure that protects neutrino masses. And indeed, based on the general logic that I talked about before, invoking John and Katie's nice work, you should think about looking for a UV theory that embeds LB minus L tau in some group that contains magnetic monopoles, and so breaks this symmetry only an exponentially small amount. Now, particle physicists know of other ways, whether or not they're good ways, other ways to get small Majorana masses that they like quite a lot. So it's even more interesting to note that this works whether or not we have right-handed neutrinos. Before I was thinking about just taking the standard model degrees of freedom, gauging this extra U1. Now, if I think about adding right-handed neutrinos and then gauging L mu minus L tau, it turns out there is still a non-invertible symmetry that protects neutrino masses. Again, the meat of it is really a Z3 subgroup that acts like lepton number on the standard model leptons, but gives neutrinos sort of the wrong charge. And so disallows now not only Majorana masses, but also Dirac masses. And now this is much more interesting because while we have the seesaw mechanism to generate small Majorana masses, and that's indeed, this is the reason that particle physicists tend to have Bayesian priors peaked at neutrinos being Majorana. If neutrinos are instead Dirac, then they have the same sort of masses as everything else. But for some reason, the Yukawa of the heaviest neutrino we know is something like 10 to the minus 11 smaller than the tau, the heaviest charged lepton Yukawa. And this is very puzzling. And indeed, I think no one will object in this room, I think, if I say that we don't really have good ways in four-dimensional quantum field theory to generate very small Dirac masses in a very natural way. But now please, tell me your favorite Dirac.
I was confused by the category.
Oh.
What is
there are some nice RS.
Quantum mechanics?
I think people are fond of some nice RS sort of ways of doing this, because you can, there's naturally some exponential localization to one frame or the other. And okay, I'm not really an RS model builder, but I think if you put the right-handed neutrinos in at the correct location in 5 dimensions, then you naturally see only some exponentially small overlap with the left-handed neutrinos. There's also there's a related phenomenon. In fact, Miriam had said some Indian had written down with collaborators a couple of decades ago that some certain stringy instantons can be responsible for exponentially small. I think they were also looking at Majorana masses, but maybe you could do the same thing with that.
So the statement is that any four-dimensional theory like this would much more naturally be described.
Well, I'd say prior to the model that I'm going to mention in a moment that we wrote down, the only ones that had the only natural ways to get exponentially small Dirac neutrino masses had been written in higher dimensional. And naturally, sort of, they seem to take advantage of higher dimensional ingredients. The warping of RS or some stringy, fundamentally stringy is. All right, by the way, please.
No, I was just saying that the 5 example that you're talking about, there can still be part of 40 examples.
Sure, there's a deconstruction.
Partial or even partially compound. Strongly double sector.
Sure,
And depending on how
that's a
which
good,
linear combination is the right thing to look at.
that's a good point.
It's not true that it's just 5 p.m.
Sure, sure, sure.
That was.
Okay, okay, that's a good point.
Yeah.
I'd say in either of those cases, you're introducing more structure than I will.
That beats my next copy.
Yes, sure.
It is kind of interesting. When I have one of these monopoles, it is kind of propagated. It's extra.
Yes, it is.
Well, the proper time, I do a loop, and it goes. I get the same propagators as particle propagator. So I get e to the minus m proper time integrated with loop.
Yeah.
Then I come back to the same. So it's funny how, I don't know, it seems like there's really one way of getting exponential higher, which is classically different.
Yeah, sure. I mean, dimensional transmutation is sort of the only good way we know how to generate small numbers. I would agree with that. And so, well, in that context, I'd say
Even this will turn out to be the
yeah, it's an exponential from the on that. Absolutely. But then I'd say in that context, the interesting thing is that this will be something again very close to the same.
But how about the seesaw mechanism? That can also generate small number.
Yeah, but from Majorana masses rather than Dirac. And I'd say maybe as a more general point, the seesaw mechanism doesn't really generate a small number, right? You take one hierarchy and you put it somewhere else. Yeah. Good. Okay, but good. So indeed, the very simple thing to do in the UV, which was always in some sense the beautiful UV completion of L mu minus L tau theories, is to look at an SU3 horizontal gauge theory, where you're putting all three of our families of leptons into a 3 or 3 bar of this new gauge symmetry. Okay, and indeed, if I go and write down in the UV only the charged lepton Yukawa, there's still a classical symmetry that protects the neutrino Yukawa, but then I go and quantize this theory, and I find that there are SU3 instantons that give me a 't Hooft vertex, which is very simple to understand. It's just one, because everything is just fundamentals, it's just one of each sort of fermion zero mode. You have 2 leptons just because L's, because they have the extra SU2L quantum number. And this produces for me a Dirac neutrino Yukawa that takes the charged lepton Yukawa and tacks on an instanton action, an e to the minus 2 pi over a gauge coupling, to very naturally give me exponentially small Dirac neutrinos in this SU3 gauge thing. Indeed, and so yeah, this is an incredibly simple field theory beyond the standard model. All I'm doing is gauging some of the approximate global symmetries of the standard model with right-hand neutrinos, but they're morally there already. So and especially because these L mu minus L tau theories had been studied for 30 years without anyone noticing it, I think it's really fascinating that this thinking about non-invertible symmetries led us here. Okay, and they're very simple. If you discover the Z prime, then really but just by measuring the properties at the LHC or whatever, you learn about the UV scale, where you see the full non-Abelian symmetry. And of course, I've really only told you so far how to generate an exponentially small Dirac neutrino mass scale. We need to generate the texture. We know from neutrino oscillations and such, but you can do that this Higgsing, and in fact, Jim Klein and Gonzalo Alonso Alvarez studied this a couple years ago. Before, in fact, we'd figured out that there was this interesting non-perturbative effect. You can do that. Okay, new stuff though. So after we wrote that down, I was for months perplexed and convinced that there must be something to discover in the quark sector as well. Because especially once you add right-hand neutrinos, there's a structural parallel between the leptons and the quarks in the standard model. The quarks are like the leptons, except with an extra SU3 quantum number. So there must be something, I felt, to discover in the quark sector as well, but it's not obvious, because if you just try porting over exactly the same thing, you'll find that the fact that the quarks have this extra SU3 quantum number means that in any 't Hooft vertex you could hope to generate, you'll have 3 times as many quarks. You'll generate some ridiculously irrelevant interaction that it seems hard to understand how you could ever get anything interesting from. In fact, what I eventually realized is the solution will be that we need to understand a more subtle notion of non-invertible symmetry. But actually, I've gotten a bit ahead of myself. What do I mean about the quark sector? We don't need to generate in the quark sector an exponentially small Yukawa. That's certainly true. But we do have this other severe problem of fine-tuning in the quark Yukawas, which is the strong CP problem. Right? And I think everyone in the room knows there are 2 places, there are 2 sorts of CP violating angles in the quark Yukawas. One is the CKM angle, which we've measured to be order 1. The other is the strong CP angle. It's related to the theta in front of the GG dual gluon term. And somehow, from studying neutrons very carefully, we've determined that that is less than 10 to the minus 10 or so. So this seems a very stark violation of our ideas about naturalness and begs some explanation. And let me remind you, because it isn't too often discussed these days, about what would have been the most beautiful way this could have been solved, which was a solution in the standard model itself, the massless up quark solution. It was realized in the 80s, early 80s, I think first by Georgia, that if you have, at some scale, a Pechi-Quinn symmetry that acts, say, just by rotating the up quark, a good symmetry, and so sets, say, the up Yukawa to 0 at some scale, then this would imply that theta bar is just unvisible in the far UV. Because if this is a good, though anomalous symmetry, then whatever theta you had in front of GG tilde, you could perform an anomalous Pechi-Quinn rotation, and you'd see that the action was changed by exactly a theta term. You could get rid of whatever phase was there. Now, of course, already in the 80s, we knew from chiral perturbation theory and matching to the masses of hadrons that the up quark in the far infrared was not actually massless. But but good, for the same reason that this works, it's a Pechi-Quinn symmetry, it's anomalous and has a mixed anomaly with SU3 color. That means that SU3 instantons violate this PQ symmetry. And by doing so, they generate a non-zero up Yukawa, a non-zero mass for the up quark. And in particular, they do so in a way which does not generate a theta bar. Physically, you can think just that the instantons themselves don't violate CP. So if you set theta to 0 in the UV, the instantons themselves aren't going to generate it. You can show that, of course, by studying carefully the running of the masses that these effects give. So this would have been the most beautiful sort of solution to strong CP, but this solution was sort of on ice for some decades because QCD, as you know, confines and we lose perturbative control over what the instantons do. So we needed to wait until lattice simulations became good enough only in the past decade or two to see how much PQ violation the instantons actually did if you could generate a large enough up quark mass. And unfortunately, you can't. The standard model itself does not bear out the massless up quark solution. But if only we had a way to learn from the infrared about some new UV instantons, and that indeed is something that a non-invertible symmetry can tell us about. And yes, another question.
Do you know how far away
Ooh.
from
It's not ridiculously far. It's like a factor of 2.
Oh,
Yeah, indeed. So really, this was something that we needed the lattice to tell us whether or not it worked.
how much do we trust the lattice?
Ooh, that's another good question. And I think at this point there's a consensus that the massive trust solution. We trust it enough that it doesn't to know that it doesn't work. But yeah, I think in earlier times when Gladys was first getting to this, there was a lot of infighting about exactly this. But now I think we know that the standard model does not bear this out. Okay.
Can I just maybe going a little bit out of the story, but so you argue that there's the lepton sector and it has this hierarchy and maybe the instantons the hierarchy, and then you said, well, maybe the quarks have a symmetry. Now, curiously, the numbers are very similar, like 10 to the minus 10, 10 to the minus 11, and we know that quarks and leptons do embed into complete things. So, is there maybe you're going to tell about this, or are there not thought about getting both from the same kind of instantons? Because it seems like you just need to generate small numbers.
Yeah.
And these two sectors do talk to each other at some very high level. So.
Yeah. Very good. Indeed, this will sort of be where I am going. Unfortunately,
I mean, there are different operators, so I don't know if that complicates things. But.
Yeah, so the use of the non-invertible symmetry in the quark sector is a bit more subtle, and you can't. It's not that like GG dual is charged under the non-invertible symmetry. Unfortunately, at least in this framework, the 10 to the minus 10 being similar is not something that is explained even if you try to unify the quarks and leptons. I'm not sure if it the people have thought before about trying to explain neutrino masses and strong CP together. But I think not terribly successful. But let me get to this. Indeed. Okay. So we need to understand a bit more subtle non-invertible symmetry.
Actually, I'm confused about the statement. The QCD is generate mass for the quark.
Yeah.
What's the What's the concept here actually?
Sorry, what's the concept? Yeah.
What are they doing here?
Yeah. So
actually, the one thing is that if I understand correctly, the issue of the state occurring is like even before you consider the scale of the below the confinement scale, we are talking about whether we can rotate the theta away even before the non-QCD scale, right? So are you thinking about scale above or below non-QCD?
Sorry, in my statements about the massless up quark?
Yes.
Well, both. You start with the PQ symmetry would be good at some high scale above lambda QCD.
Right.
Yeah.
So we are talking about the mass which is more close to the bare mass that you write in the QCD Lagrange, and
Yes.
before we consider any QCD, like a confinement,
Yeah.
non-QCD, this type of a strong dynamics.
Yes,
right?
yeah.
So-
You want this PQ symmetry to be good at some high scale.
That's right. So then what's the QCD?
Yeah, good. So QCD instantons generate some large tough vertex.
Yeah.
Yes.
Okay.
And
this is different from the confinement or the mesons and the baryons. Those gather some mass due to the QCD interaction, right? This is different thing we have been involved.
I'm not sure I could tell you exactly how different without winning the Clay mathematics prize.
Yeah, I mean, we need to solve the problems in the sense like you are solving.
Yeah, I mean, it's not like binding energy of a meson. That's certainly
That's
true.
different. From
But-
yeah.
But the extent to which instantons do that as well, I think is, I don't know exactly what to say about it. But anyway, sorry, the picture is that SU3 has instantons that violate this PQ symmetry. And so, some of these legs are the top quark. And you can close this off with an insertion of the Higgs VEV, right? And similarly, everything else. So even if you started with no mass for the up quark mass were set to 0, then SU3 instantons in concert with electroweak symmetry break-in would generate some sort of mass for the up quark.
And this will happen if that work need to happen above the electroweak scale or even
No.
something above
In the far infrared, right? You expect the largest effect of these SU3 instantons should be as SU3 is confining, and the coupling is getting very strong.
All right, measure.
You'd
Because of the, not to go full match ones, but is this like the SBR mass?
no, this is like the ratio of I forget which hadrons are which. But the ratio of a hadron with some U quarks and a hadron with some alphas. Yeah, exactly. And that's the sense in which already when the massless up quark was first suggested in the early 80s, we already knew from current algebra and such that there had to be some effective mass generation. Good.
Yeah, okay.
Yeah. Good.
I think that let me just try to clarify because
Sure.
I think the way I understand the problem is like you start with some QCD, maybe bare Lagrange, writing on some high scale that you do the QCD lattice simulations.
Yeah.
And there you do have some input from electroweak Higgs field with some that. So from the QCD, I think sorry, the QCD lattice simulations probably starting at some energy scale like 2 GeV if I check
Sure. Yes.
on this
exactly.
particle data group. 2
That's right.
GeV.
That's right.
And that certainly is much below the electroweak.
Indeed. So the quarks are already massive. The other quarks are already
Right.
massive.
So there the issue is like suppose we put some input, some mu, the U quark with some mass. Let's say we don't really know about, we want to start with something mu as input.
Yeah.
And we run the latest QCD and then run to the nuclear non-QCD scale and try to match the spectrum
Indeed.
of the nucleons.
Right.
And we find that it cannot be 0 for
Indeed.
mu.
Exactly.
Right. So the input there for mu is about 2 GeV.
Yes.
And now you are telling me that perhaps there's some QCD effect, generate some mass to the mu. But that's not come from the Higgs coupling, the Higgs coupling. So your quark is still can be 0 for your quark. That is scenario of the problem. And then
Well, sorry. You mean this standard model massless up quark?
yes,
Or-
if you want to use the instanton to solve the strong CDC.
Yeah, but so there definitely is a contribution to the up quark mass from the instantons, right? up quark Yukawa or the up quark mass that you put in at 2 GeV is not exactly the same as what you infer from infrared hadron spectroscopy, because there is some contribution from the instantons. But if the instantons could make up all of that mass, then there would have been this Pechi-Quinn symmetry, and you would have had an explanation for why theta bar was 0. But it's not. Unfortunately, the standard model doesn't work that way.
But you say it's theta bar factor 2.
Something like that. Yeah.
Okay.
Yeah.
Okay. Great.
Great. Okay. So
let me just mention, but there's also a different mass mechanism which we call symmetry mass generation.
yes,
So which may make up, if they can contribute half of the contribution.
sure. If we find that there are extra 4 quark interactions or absolutely. This is one idea just in case that one doesn't end up being just so we can know all the possibilities.
I'll continue
Thank
but thank you.
Yeah, we should talk later. Good. So non-invertible symmetries are not just don't just appear in U1 gauge theories. Indeed, in a U1 gauge theory, the instantons in general take integer values, but there aren't any on R4. They only exist if you look at something like S2 cross S2, something where you have a 2 cycle. And this is what we were taking advantage of to construct a non-invertible symmetry in that case. But that's not the only such interesting case. If you have some SUN group, then you have all of the instantons that there are, you have on R4. But you can have a case like SUN mod Zn, so QCD with adjoint matter, no fundamentals, then in fact, there are some instantons on R4, the integer values, but there are extra instantons that don't exist on R4, but only on something like S2 cross S2. And again, that's another case where you have an ABJ anomaly, but some of the instantons that would sort of dynamically do this violation for you are Miffy on R4. And in particular, in the quark sector, specifically because we have the same number of colors and generations, if I write down a particular horizontal quark symmetry, where before we were talking about a horizontal lepton symmetry, LU minus L tau. Now if I take, say, B1 plus B2 minus 2 B3, a horizontal baryon number symmetry, then again, because minus 2 is equal to 1 mod 3, I can have a non-trivial global structure here. And again, this bears out a case where there are certainly SU3 instantons on R4, but this theory will have some fractional instantons that don't exist on R4. Now the time is getting late. Thankfully, the right way to compute this in full generality was kindly explained a couple years ago by Sung Woo and his collaborators Mohammed Anbar and Minho Sung. And what you want to do is go to S2 cross S2 and turn on all of the allowed background fields and look at what sort of fractional instantons you can get, and compute when you have access to all of these instantons, what sort of violation of the global symmetries you would get, and just being on R4, these turn into non-invertible symmetries, the ones that are broken only by instantons that exist just on S2 cross S2. And indeed, I'll spare you all of the messy calculation, but when I have this non-trivial global structure, indeed, because of these extra fractional instantons, there's a Z3 non-invertible symmetry in the quark sector that exactly mirrors the one in the lepton sector. It acts like baryon number on, say, Q and U, but has the wrong sign for the down quarks. So prohibits or protects all of the down quark Yukawas. Okay. And in fact, this is the possibility of this non-trivial global structure is even a bit more striking if I sort of uplift a bit. I could have thought about writing down an SU3 horizontal symmetry in the quark sector, just in the same way I did for the leptons. And if you write down the charges, you'll notice the peculiar fact that the charges are exactly the same as they already have for SU3 color. And so the gauge group can actually be SU3 cross SU3 mod Z3 because you don't have any matter that's being charged in one and not the other, or in the wrong combination, something like that. Good. Now, what does this point to? This points to the fact that you can write down this unified theory that somehow has seen essentially zero study of color flavor unification, an SU9 theory in which you sort of interweave the colors and flavors together into the fundamental of SU9, all of the colors and flavors of quarks in the fundamental. All right. And then now I can just sort of mirror the structure of the lepton theory. I write down the top Yukawa, and now you'll note in this flavor symmetric way, it makes more sense to start with the top Yukawa and generate the down type Yukawas from instantons. So I write down just the top Yukawa. So there's manifestly a Pechi-Quinn symmetry in the far UV. That means that beta bar is unphysical. But then the instantons generate, just like they did in the lepton sector, generate the down type Yukawa formula, the same sort of way. And this is just like the structure of the massless up quark solution, except here we don't have confinement to worry about. But it's not. Let me remember what my next slide is. Okay, and there's some interesting structure to point out that usually we don't see in grand unified theories. That it's a special sort of embedding. So there's a non-trivial index of embedding. What this, it's sort of, you can think of it like an outer product, right? You're sending the 9 into like a matrix, a 3 by 3. And this means that since the fundamental branches to the bifundamental of SU3 cross SU3, the Dinkin index that you would calculate, sort of the number of legs of this representation that you would calculate an instanton having, the number of zero modes that the instanton would have, changes non-trivial. You get 3 because you have sort of 3 fundamentals for an instanton of, say, SU3 compared to the 1 for the fundamental of SU9. And this means that you should think of the 1 instanton in the color instanton as actually being the 3 matching onto the 3 instanton of SU9. And so you know, this matches on to your the intuition you might have about non-invertible symmetries. It's talking about some extra instantons that exist that are sort of color instantons. There's a fractional instantons of SU3. And the important thing to mention for phenomenological applications is that this means that the gauge coupling gets matched quite non-trivially across the SU9 breaking scale. You need to match the 1 instanton of SU9 onto the 3 instanton of SU3. And so there's a factor of 3 rescaling. Thinking from the bottom up, you get a factor of 3 stronger into the UV. Please.
This gives you a hierarchy. So this gives you a small mass for one of the quarks. Does it give you a hierarchy between like several generations?
Good. So so far, what I've sort of done, and I'll tell you on the next slide, and indeed you need to be careful more. So far, everything is still flavor symmetric. Going from SU9, it's color flavor symmetric, but then to SU3 cross SU3, I still have the horizontal symmetry. So there's just one up type Yukawa and one down type Yukawa. So what I'm really trying to do is generate the bottom from the top. Indeed, just like in the lepton story, you need to think about generating the entire matrix. And I'll talk about that in a moment, because as you probably rightfully have in mind, it's more severe of an issue in the quark case. But just to say that in the lepton case, I wanted to generate 10 to the minus 11 or something. And so I could just think about the exponential of the instanton and not really care about the polynomial prefactor. And now, yeah, I am trying to generate 1/40 or something. So I can't just think about the exponential. I need to be a bit more careful about what the instantons actually generate. Thankfully, remarkably, Tufts did this in 1976. If you haven't seen that paper, it's gobsmackingly amazing that someone could do this that long ago. You have to integrate over all the zero modes, determinants and such, and solve for what the actual fermion zero modes are. And indeed, this analysis, I should say this is preliminary, but this analysis, and there are further caveats as well, would tell you something like 0.25, alpha of 0.25 to generate this sort of hierarchy. It does need to be quite a bit stronger. Okay, and that doesn't sound so bad, except that then I perhaps remind you that in a large N-gauge theory, really the counting parameter is the Tufts coupling, so n times alpha. And then, okay, alpha 0.25 also isn't trustworthy. So really, we're going to lay out in this paper, hopefully, when we write it, when we finish it, the structure of these theories. But again, we're going to have to rely on lattice simulations to tell us actually in a trustworthy way whether you can get large enough instanton effects. But I think, well, because this is some UV physics that we have control over as theorists, I think you can hope that there's some range in which it works. And it's interesting to know that sort of structurally the ingredients are there in the standard model for extra instantons at this color flavor unification scale. But indeed, I can't claim to have really solved things until we get some more input from lattice simulations of SU9. But let me address I think my next the gauge coupling needs to get a bit bigger into the UV. That's natural. We're going to need to generate the right flavor stuff, some vector-like quarks to come in at, say, the scale at which you see this horizontal symmetry. So it's very natural for that the extra charge degrees of freedom there to flip the beta function and for things to initially get stronger before, again, becoming asymptotically free above the SU9 scale. Now, I do really need to address how to generate the CKM matrix, because if I told you I could set theta bar to 0, but I didn't tell you how I could generate the phase in the CKM matrix, I'm not really solving anything at all. And indeed, there's rather a puzzle here if you're not thinking about it. I was not thinking about it correctly for a long while, because, okay, we're going to break this horizontal symmetry with, say, some adjoints. And so you'd be tempted to just say, okay, I need to generate some more structure in the quark Yukawas. I'll just write down some dimension 5 operators to do that. But if you just wrote that down, then that would imply that these Higgs's are actually charged under the Peccei-Quinn symmetry. And so when they condense, they would break it. And we to get a mass subquark solution, we want that the only breaking of the Peccei-Quinn symmetry is from the anomaly, from the instantons of this gauge group. So this would upset our solution. There's some interesting phenomenology to work out, maybe about some heavy QCD axioms, but at least I'm more interested in understanding that you can do a mass subquark solution. But it's still a puzzle. How do you generate extra structure in the matrix without also breaking Peccei-Quinn symmetry more with some whatever Higgs's you want to enter there? Well, the point is that we've already broken the Peccei-Quinn symmetry at the very high scale. We don't want to break PQ anymore. We just want to sort of transmute how that enters into the flavor symmetry. And so the way to do this is using some vector-like quarks. And then with the vector-like quarks, you can write down a marginal coupling of these flavor breaking Higgses to the quarks without having it be charged under the Pesci-Quinn symmetry. And so you automatically, you end up with that dimension 5 operator in your effective description, but automatically, because how you generated it, it's proportional to only the one PQ violating spurion, which is from the instantons. And indeed, just with just introducing just simple vector-like fermions and not saying anything else, you can generate a general CKM matrix. It's not a beautiful theory of flavor. I think these are some new unified theories of color flavor unification we're writing down. I hope that they get some attention from really people who've been thinking about flavor model building for decades now. And it would be fantastic to understand a really beautiful theory of flavor in this framework. But at least as a proof of principle, you certainly can get whatever CKM matrix you need without upsetting that theta bar is 0.
You said heavy axiom, how heavy is like, is this going to be accessible or depends on the scale of?
Good. I haven't thought enough about the heavy this phenomenology to give you a good answer. It would get an extra contribution to the axion potential from the SU9 scale. So maybe to the extent that this is at least above a theory of flavor, it has to be 1000 CV or more. So yeah, maybe too heavy for LHC phenomenology, but I'm also not super familiar with how that all works. I think there was another question.
Beautiful, is that a technical thing? Like, I'm using it as
here to get the here to get like the down part we call it. Yeah, I mean here I haven't. It's not good. This theory of flavor does not improve over just putting in the colors by hand and having to put in the small numbers by hand.
You're saying if I take it on the song,
Yeah, that's good. If you want to think about naturalness the correct way, then yes, that's right. Yeah. Okay, let me mention just by chance, not by chance, but in the last moment, I went over just because it was sort of conceptually easier going from SU9 to SU3 squared down to SU3. I started this section by talking about the SU3 cross U1 theory. And indeed, I think actually the more phenomenologically promising route is to go straight from SU9 to this theory down to SU3, because, well, for one, this can be at a much lower scale. This doesn't sort of have tree level, well, no, be careful with that term, but it's not enormous flavor changing neutral currents at this scale because it's a U1. So this could be at LHC accessible energies. And it also, I think, the instanton density might end up working better. There's more to understand in this scheme. But let me conclude. Thank you for your attention. I think as particle physicists, the general lesson is that these quantum field theories that we care about have higher dimensional operators, they have generalized symmetries, and it can be useful to understand them. Learn interesting things about possibilities for UV physics. And in particular, what I told you about is that these gauged horizontal symmetries, which to some extent people have been playing with since the 80s, there's interesting non-perturbative physics in these theories that no one had noticed. And they can really connect to some infrared problems of the standard model. And I find it especially intriguing that 3 generations has some special structure there. There definitely needs to be more phenomenology, and toward the question that was asked, further into the UV, you'd like to put both of these together into an SU12 Patty Salam model and get a common explanation for that. Could be future work, and I think there's lots more to do. I'm grateful that Juven has had such an interest in pushing generalized symmetries in general and in connecting to particle physics. I think there's lots more to do here, and I'm excited to see where it goes. Thanks very much. Thank you, Jim.
Question, comment also on my audience. Using feel free to ask.
We have lots of questions during the talk, and I'm sure we'll talk more over the next couple of days.
We'll wait for
Yeah. I'm happy to take questions online as well.
Online audience, any questions?
It's like one each. There, that have applications for like specific like flavor observables that we actually measure so far. In the same way that it would in like context of like a frequency model.
I'm not sure if I have a great answer for that. Yeah, I mean, sorry. It's good because it has a structure of 1, 1 minus 2. Then it's saying that it allows mixing only between two of the generations. This is a very generic statement. I don't have enough flavor stuff in my head to tell you exactly which observables that might map onto it. But indeed, I think there's some flavor modelability, flavor physics to be done there. And it doesn't, I just did 1, 1 minus 2 because well, people often think about the third generation being the special one, but it could be any cyclic, any such combination. Yeah, I don't know which is most promising for the B anomaly, so whatever you might want to do. Good question. I can check if there was further. Okay, it doesn't look like any questions online.
I almost said what you.
Oh, yeah.
Then I realized, I remember that. There might be.
Yes. Well, some of them are still there, right? Okay.
Yeah.
I don't. Cool.
Okay, thank you very much.
Yeah. Thank you guys. Okay.